Alright, hey everyone! Okay, so I want to talk about the Descartes rule of signs today. Okay, so Descartes rule of signs, again, it expands on roots and zeros with polynomials. Okay, so let's read what it says. So it says we have a polynomial with real coefficients. That's the key word here. The number of positive real zeros of this polynomial is the same as the number of changes in sign of the coefficient of the terms, or is less than this by an even number. Okay, now what this means is that, remember we said that we could have at least one zero in the set of complex numbers, and this was by the fundamental theorem of algebra. Okay, so but if I just want to figure out what the real zeros are, be it a positive real zero or a negative real zero, I'm going to refer to the Descartes rule of signs theorem. His rule. I'm going to refer to Descartes' rule of signs. And Descartes actually comes from René Descartes, which is that French mathematician. Yeah, so I believe he's the one that he said, I think, therefore I am. Alright, so he made a rule of signs. He was also a mathematician, so a philosopher and mathematicians, they usually go hand in hand. But anyways, this is not a history lesson. We want to learn about his rule, and we want to see what he's offering to us in algebra and how this can help us solve our problems. In math, of course. Okay, so let's see. So the number of positive real zeros, so again, it's the positive integers, positive real zeros, positive whole numbers, positive fractions, whatever they are, positive, as long as they are positive and they are in the reals, okay? Then it depends, or is the same as the number of changes in sign of the coefficient of the terms. So as the coefficient, so here's our first coefficient, it changes in sign, then the number of positive real zeros is going to be less than that by an even number. So let's say you have 3. Okay, you have 3 changes in coefficients. The number of sign changes 3 times for your polynomial at x. Okay, the key word is that it's at x. Then it's less than that by an even number. It's the same as the number of changes, or it's less than that by an even number. So 3 is possible, then 2 is possible, and then 0, the number, of course, number of real roots. Either 3, 2, or 0. And then the next one is if I want to figure out the negative real zeros. Alright, it's either this, again, I'm counting the number of changes is the same thing as the first one, except now I want to, so it's the number of changes in sign of the coefficients of the terms, but this time I'm plugging in negative x. Here I didn't touch x at all. X stays the same, but now I'm doing it for negative x, and it's less than this by an even number. It's either the same or less than this by an even number. Right? Remember, roots come in pairs, right? You know how we always do the plus or minus whenever we did our quadratics? And I'm using quadratics because that's something easy to visualize for us right now. It's so it was always plus or minus. So again, roots come in pairs because of that plus or minus in the square roots. Okay, so now let's look at an example. Let's see Descartes' rule at work. All right, let me see if I can zoom out a little bit. And I'll bring this up. Okay, state the possible number of positive real zeros, negative real zeros, and imaginary zeros of the polynomial negative x to the power 6 plus 4x to the power 3 minus 2x squared minus x minus 1. Okay, so first things first, for the positive real zeros, because I'm going to use the Descartes rule of signs. First I'll figure out positive real zeros and then my negative real zeros. And it's, again, Descartes talks about the real zeros, and we use this with real, if we want to figure out what the reals are. The real zeros, the real roots, x-intercepts, whatever you want to call them. Alright, so for the positive real zeros, using Descartes' rule of signs, I'm going to just use p of x. So everything stays the same, so it's going to be negative x to the power 6 plus 4x cubed minus 2x squared minus x minus 1. Okay, now change in coefficients. So coefficients are the numbers in front of our x term, right? So this goes from a negative to a positive. So this is my first change in sign. Okay, I was combining change and sign together to make sign, but that doesn't make sense. All right, so it's negative 1 to 4, positive 4. So here it is. I have a change in sign. We'll just go ahead and say yes. Y for yes. We have a change in sign here. And then I have positive 4 to negative 2. I also have another change here, so I'll put yes. And then I have negative 2 to negative 1. I don't have a change there, so I'll put no, because they're still negative. And then from negative x to negative 1, which is a negative 1 coefficient, and then I have negative 1. This is not a change, so I'll put no here. Okay, so I have two changes in sign that are happening here. So I have, what is it? The number of changes in sign here, in the signs, is 2. Okay, so here it equals 2. But by the Descartes rule of signs, it says that it's either the same as the number of changes, so it's either 2 or less than that by an even number. Well, 1 isn't an even number, so the next even number is 0. So it's either 2 or 0 real zeros. Okay, positive real zeros. Let's add that in. So number of changes is either 2 or 0 because I only had it happen twice. Now, if I'm going to scooch this down a little bit more, now let's figure out the negative real zeros. So, but to figure out the negatives, alright, so let's write negative real zeros. It's going to be p at negative x. Now I'm going to do it for the polynomial at negative x. So it's going to be negative times negative x to the power 6 plus 4 times negative x to the power 3 minus 2 to the times negative x to the power squared minus x minus 1. Right. Oh, and it's actually negative x. Let me fix that real quick. So it's minus negative x. Okay. And then, so when you solve all that out, going lower, it's going to be, so anything that is in even power stays the same. But again, you had a negative out here, so it's negative x to the power 6 plus, right before I write that down, I have x to the power, negative x to the power 3, and then when you have it to an odd power, it actually changes its sign, so it's negative 4x to the power 3. And then I have a negative to an even power, so that's going to stay the same. It's still going to stay x, so it's minus 2x squared, that stays the same. Again, even power. And then this is an odd power to the power 1, so it's basically negative times negative x. So that's going to be positive x, because negative times negative is positive. And then minus 1. You don't have a negative x there to plug in, so it just stays the same. It's a constant. Now you're going to find the number of changes on for this polynomial. Okay? So the number of changes that are occurring here, I go from negative to negative. Well, there's no change, so I'll put a no, and for no. And then I'll go from negative 4 to negative 2. Again, I'm just looking at the coefficients. I don't see anything happening here. It's still negative, so no change happening in those coefficients. And then we'll go from coefficient negative 2 to positive x, right? It's going from negative to positive here. So yes, I have a change happening here. And then I go from positive to negative. So yes, I have a change happening here. So the number of changes in sign that happen for negative real zeros now, it's either 2, it's at 2, because I have 2 right here, I have 2 yeses. And it says less than that by an even number. This is the key word here. Less than that by an even number, so again, it's either 2 or Just like our positive, it's either 2 or 0. So I have it either being 2 positive reals or 0 positive reals, or I have 2 negative real zeros. So these are negative real zeros that we have. Or 0 negative real zeros. But then what about our imaginary? So how could I write this out? Okay, so your next step after you've done the Descartes rule of positive real zeros and negative real zeros. We found that you could have 2 positives or less than that by an even number 0. Same thing with our negatives. It was the same thing in this instance. But the next step that you need to do is you need to create a table. So we'll have the number of positive real zeros. And then we'll have, right? Then I'll have the number of negative zeros, negative real zeros that exist. And then I'll also have the number of imaginary zeros that could exist. But remember, Descartes' rules didn't tell us too much about imaginaries. But if you know the your positive and negative real zeros, how much those could exist, then you can tell how much imaginary zeros could exist. Because by one of the previous theorems that we learned about in the roots and zeros video was you can find the total number of zeros, and your degree was the n number of zeros. Your degree n tells you the number of n zeros that you're going to have. Okay, so total number of zeros. Okay, now look here what happens when we make this table. So the number of positive real zeros, again, I could have 2. So, but what's our degree here? Our degree here is 6. So I have to have a total of 6 zeros at the end. Has to be 6. Alright, so if I have 2 real zeros, and I could have 2 negative real zeros, then the number of imaginary zeros would be 6 minus 2, which is 4, and then 4 minus 2, so what remains is 2. I could have 2 imaginary zeros, because then if I did 2 plus 2 plus 2, it equals 6, so it adds up. So this is one possible combination I could have of my zeros. Now the next combination, now imagine we had 0 positive real zeros. Okay, then that would mean, or it could mean, that I have 2 negative real zeros, alright? Because this is a different combination. Alright, it looks like it does look like we're dealing with some probability over here. Alright, so number of imaginary zeros. Alright, again, you want your total to equal 6. So 6 minus 2, how many more zeros do you need to make up for that? Then you need to have 4 imaginary zeros. Alright, so basically the positive real zeros, the negative real zeros and the imaginaries, they all make up for how many zeros you have to have at the end, which is a total of 6. Alright, so we did a positive of 2 and we did a positive real zeros of 0. Now let's change it back to 2, but this time we'll have 0 negative real zeros. Okay, so how many imaginaries should I have? Just like the combination on top right here, I should have 4 imaginary zeros, because 2 plus 4, I want 6 eventually at the end. Now, let's do it for 0 positive real zeros, but this time I'm doing it for 0 negative real zeros. So if I have, because that was a possibility, I could have 0 positive reals, and I could have 0 negative reals. And if I had 0 of each, then how many imaginaries do I have left? I have to have 6 imaginary zeros, because I still need a total number of 6 zeros. Okay, so, alright, this is how we would use Descartes' rule of signs to show if we have positive, negative real zeros, imaginary zeros, and the total number of zeros, which comes from the corollary of the fundamental theorem of algebra. Okay? Alright. Thank you for watching.